Okay, so in a nutshell, as Tim said, gravity field is a vector. It's a three component, gx, gy, and gz, and we always measure classic conventional instrument measure the vertical, the gz component. And what we do with gravity gradiometry is that we measure the three vector, we measure their rate of change in the three direction. So we end up with 9 measurements, which is a hell of a lot of information, but that's good. The more information we have, the best it is. So that's the difference. And a very simple way of explaining what we do is it's not the black box. There's no magic science. There we have accelerometers on board. That's what we do. Your iPhone has accelerometer on it too. So that's exactly what we do. When you have something denser and you fly over it, it's going to make your accelerometer spin faster. And that's how you record that pull in a gravity field. When you have a single accelerometer, you get the gravity. No, if you have two mounted on the same platform and you measure the difference between the two, well, you measure a rate of change of the acceleration. And that's what we do with gravity gradiometry. And there is another great advantage of measuring difference between pairs of gravitators is obviously we do airborne survey. We want to measure something which is really tiny, and we fly in something which is moving a lot and quite fast. So the aircraft would be the same if you were doing it in a car. The vehicle has its own acceleration, and it creates a lot of noise. Actually, the noise, the acceleration of the aircraft is far superior to the acceleration we're trying to measure. So going back to those opposing pair of accelerometers, the great thing about it is that by taking the difference, they're not far apart. They're only 30 centimeters apart. So the noise they record in position A, position B is almost the same. So by taking the difference, we kind of remove the noise of our platform, of recording platform. So that's really the great trick here in the measurement.